Okay, let's continue with different types of mathematical models. Here, the second type of mathematical models is static models and dynamic models. Okay, for static models, they are time invariant, which means that the relationship addressed by this model doesn't change no matter how time changes. Models that the system in equilibrium or steady state. Output of model depends only on current input because it doesn't. The relationship doesn't change across time by time, right? Modeled by equations with static variables. For example, fx is equal to v. Let's just assume that fx is a function to address speed of your car. If you're driving at a steady speed, then you can simply use fx equals v to represent your speed. Your speed is v and it doesn't change by time. It's a static mathematical model. But what if your speed, the speed of your car changes by time? So at the very beginning, you have a speed of v, and this v changes by time. X is time. X is time. Okay. So if your speed changes by time, then this function changed from v to v plus the change of your speed by time. So you can see for this static model, it has nothing to do with x, although the independent variable here is x. But since it doesn't change, the speed doesn't change by x. X is time, right? So x is actually not there in this model. It's simply v. But here, if your speed changes by time, by x, then x should be here to address the change of your speed. So this is a dynamic mathematical model, okay? It's time dependent, accounts for time dependent changes in the state of the system. The system is your car, and when the speed of your car changes, this model should be able to address it. Output of model depends on current and previous input, right? You have an initiate speed, and that is the previous input, or you can say that's the initial state of your model, and you can consider time as the input, and as the time changes, your speed also changes, right? So your output, which is speed, changes. Often modeled by differential equations with variables expressed as a rate of change. Here, this part, the second term of this dynamic model, is used to address what? To address a rate of change of speed by time, the change of v by x. So this is a dynamic model. And next, let's talk about explicit and implicit mathematical models. For an explicit model, input parameters, they are known. Output parameters need to be solved, and output parameters can be calculated by a finite series of computations. Right here, y equals fx. X is the independent variable, is the input, and y is something we want to calculate. It is the output of the model, and it should be able to get calculated by this model. So we know x, we calculate y. On the other hand, we have implicit model. It means that we know the output. For example, this is a function about x and y. They are both independent variable. We don't know them. They are unknown. But we know the output. The output is 0. So we need to find out a way to solve x and y when output is given. It is an opposite scenario of the explicit model, right? For explicit model, we know input, we want to solve output. But here we know output, it is 0. We want to find out the input. So it's implicit model. So output parameters are known. For this specific example, the output is 0. Input parameters unknown must be solved for by an iterative procedure, such as Newton's method or Boyden's method. It means that you cannot simply use one step to find out the input. You need to repeat this solving process multiple times using PCAs to get the results, which are inputs, right? And here is an example from remote sensing. It's called spectral unmixing model. Okay, so in remote sensing, in a remote sensing image, each pixel is representing a specific area in the real world, right? For example, we have a pixel with 3 land cover types: impervious surface, soil, and vegetation. Or for example, let's just assume this pixel covers a 30-meter by 30-meter real world area. Okay, there are impervious surface, there is soil, there is vegetation. So here we know the output. This is the result. This is the result, right? We have 3 end members, or we say we have 3 land cover types: vegetation, impervious surface, and soil. The question is, what's the abundance of them? From this specific figure, we know that impervious surface accounts for 50% of the pixel. Soil maybe 20%, vegetation 30%. But how to solve this mathematically? We know there are 3 land cover types, 3 end members, but this is the output. We want to know the input, right? This is a very typical example of implicit model. We know the output, we want the input. So I'm not going to give you details, but by the end of this model, or a spectral mixing model procedure, when we finish this unmixing process, we have results, right? Vegetation is 40%. Impervious surface is 50%, soil is 10%. This is what we want. This is the input. At the very beginning, from the image, we know the output. There are 3 land cover types. There are 3 end members. But what's the abundance of them, right? Implicit model. At the end, the results are inputs. So there are also discrete versus continuous models. For discrete models, in a discrete model, it treats entities as discrete objects. For example, you are a doctor and you have a patient in favor, and you need to measure the temperature of this body temperature of this patient every 30 minutes, right? At the noon, you take the first measurement. Then 12:30, the second measurement, 1 o'clock, another, and continuously until the midnight, right? Then you have a lot of sample points or measurement points. At each point, there is a specific time and also the corresponding body temperature of that patient. If you put all these points in a 2-dimensional plot, you will have a scatter plot. And in this scatter plot, you don't have lines, you have points. Each point has a coordinate for time, another coordinate for temperature. So each point is independent. Or you can say all those points, they are discrete because they are not connected, right? Because you do the measurement every 30 minutes. So this is a discrete model. There are also continuous models. They treat objects as a continuous fields, For example, when you're driving, there is always a speed meter from your car. And it means that the car itself, the computer on the car, is monitoring the speed of the car continuously, non-stop. This is a continuous model. So here we have examples. Sorry, the sequence here is is not consistent with the text here. At the top, this model is a continuous model. At the bottom, here is a figure to show you the discrete version of this continuous model, right? Here at the top, you can simply use this scatter plot to address the example I mentioned for the body temperature of the patient, right? If you consider the vertical axis as time, this is the first measurement at a specific time, and the y or the horizontal axis is for time. A vertical axis is for temperature. At a specific time, there is a measurement for temperature, another measurement, and each measurement is a discrete point, right? You can just address all those points in this scatter plot. You have this discrete model. And again, if you're using a speed meter to monitor the speed of your car from time t0 to time t1, this monitor is nonstop. Okay, so eventually you don't have a bunch of dots or points. You have a continuous curve like this, right? So in this model, the vertical axis is for speed. For example, miles per hour, right, or kilometers per hour, but still the horizontal axis is for time. So discrete model, continuous model. And we also have deterministic versus stochastic or random models. For deterministic models, randomness is ignored, which means that if you gave me a specific input, I gave you a fixed output, no randomness. Every state is uniquely determined by parameters in the model and by sets of previous states of these variables. So here is an example. This is the model. Let's say it's a function fx. For example, you can be more specific. Fx is equal to a plus b multiply x, right? It's the easiest, simplest linear model. You give me a specific x, you multiply that x by b, then plus that result by a, and you have the output. So with a specific x, you have a fixed output. That's deterministic model. But there are more complex models. They're closer to real world. They're more complex. They're called stochastic model or random model. Randomness is explicit. States are not described by unique values, but rather by probability distributions. For example, we still have 3 inputs, and each input is not a variable, is a possibility distribution. It means that, okay, for x1, it could be anywhere from, say, 0 to 2.0. It can be any value between these two values. And for a specific value between these two values, there is a probability. For example, although it can be anywhere from 0.0 to 2.0, but the probability of getting a 1.0 is 50%. But the probability of getting a value of 1.5 is only 30%, which means that the input is not decided. And after using this model to predict the output, again, there is no fixed results. There is no fixed output. You still use a probability distribution to address the output. For example, I don't know if you should have a value of 3.0 or 4.0 as result, but I can tell you that it's 50% probability that you will get an output of 3.0, but only 30% to get an output of 4.0. Okay, can you see the difference between deterministic and stochastic? In stochastic model, this model does not provide you with a fixed result. It gives you probabilities. Okay, it's more complex, but it's closer to the real world. And in this course, we focus more on stochastic models. Okay, so you should establish this type of mindset that the output of the model is not always something fixed or settled or decided. Okay, it should be a probability because it's closer to the real world. It's closer to the real world. And we also have empirical models. It's also a type of models. Okay, models. We introduced mathematical models, right? Now let's talk about empirical models. They use empirical observations to construct a statistical model of the relationships between variables. Okay, be careful. It's statistical model, which means that these models, they simply address the statistical relationship between two variables, but they ignore the reason why this relationship was established. I only care about your relationship, but I don't care. I cannot address how you established this relationship or if there is causality between these two variables. Okay, this is pretty important. So advantage do not require much knowledge about the processes behind the phenomenon. Right? This is just another expression of the fact I gave you. These models, they cannot address how this relationship between two variables was formed or whether there is relationship. No care, no care. If you give me two data sets, I will try to find out if there is statistical relationships between these two data sets. It's relatively easy to build. It's accurate locally. Okay, and the problem is that these models, it do not consider the processes that gave rise to the observed relationships. Right? There is also interpretation issues, correlation versus causality. Be careful with this. Correlation does not mean causality. Okay? Okay. For example, here is a figure showing two things. Red is for per capita consumption of mozzarella cheese, red curve, by time from 2000 and 2009. And the black curve here is for civil engineering doctorates awarded from the same time period of 2000 to 2009. Okay, the left vertical axis is for the consumption of the cheese. The right side is number of degrees awarded during these years. If you compare these two curves, you can tell that they are positively correlated, which means that as the consumption of cheese increases across time, the number of civil engineering doctorates awarded also increases. So obviously you can use these two curves to create a very accurate empirical model to address this statistical relationship between these two variables. But can you say that there is causality? Can you say that the increase of cheese consumption leads to the increase of number of civil engineering doctorates awarded? Obviously, you cannot, because we know that there is no correlation. There is no causality. These two variables, they're correlated for sure, statistically, but there is no causality. One does not cause another one. Okay, so this is the tricky part about empirical models. You can establish pure statistical relationship between two variables, but that's it. It only works for these two variables for the data you have. It means that this model works locally for a specific area or for the data you have. But beyond that, you don't know. You don't know if the relationship still stays. And no need to say that you don't know if there is causality between two variables. In order to figure out that, you need to do more experiment. Okay? Okay. So next, this is the main character of our course, simulation models. Okay. Computer iteratively recalculates the system state as it changes over time when we're using simulation models to address real-world phenomena. Instead of solving equations representing the system, we simulate the evolution of the system over time, which means that we care how the system works, how the system evolves. We do not care so much about the output of the system. We do not care that much about an accurate result or a specific value. Instead of that, we value what? We value the possibility. We value the randomness during the change of systems. And there are two major types of simulation models. The first type is called macro level. Usually, if a simulation model is at macro level, it's called systems dynamics model. Or we can care about each individual in this system, because at macro level, we only care about stakeholders, different groups of stakeholders in this system. But at micro level, we care about each individual, or in this course, we care about each agent in this system. So if you're addressing, you're creating a simulation model at micro level, in this course, we call them agent-based models. Okay, and specifically, we use something called cellular automata. I'm going to introduce this very important concept later, okay? But for now, you just need to know. We use cellular automata to address the simulation of the system at micro level, okay? And agent-based models, they are spatially explicit. Macro level models are sometimes called spatial simulation models, okay? So agent-based models, they're also called simulation models or micro-level simulation models. So here is an example. Here is an example for systems dynamics model, okay? Which means this model is created at macro level, which means we do not care so much about individuals. We only care about different types of stakeholders. For example, in this model is used to address the relationship between prey and predator. So there are different types of say components of this model. So we have stocks, system variables, right? Now we have actually how many stocks? Two stocks. One is prey population, another one is predator population. We also have flows. This concept here is very tricky, okay? Be careful with that. They are for movement of stocks. So pre-birth, this wide arrow on the left is a flow. Pre-death, that's another flow. Predator birth, the third flow. Predator death, that's the first flow. We have four flows here, okay? And we also have other solid arrows. They are not flows. They are addressing the relationship between different parameters and stocks, okay? Okay, so the flows, they are only for movement of stocks. We have 2 stocks and 4 flows. Okay, parameters are other variables describe the overall state of the system. For example, pre-birth rate, pre-mortality, right? Predator consumption of prey. You can say these parameters, they are connected by solid arrows. These arrows, they are addressing the relative relationship between parameters, but these solid arrows, they are not flows. These 4, 1, 2, 3, 4. 4 empty or 4 wide arrows, they are for flows. So let's check out this model again. Like I said, this model is created at macro level, which means that individuals are not that important. So that's the reason why here we only have pre-population and predator population, these 2 stocks. We do not care about the specific relationship between each individual prey and each predator, each individual predator, right? So this is a simulation model at, say, higher level, systems dynamics model, right? And we also have this. We also have agent-based model. Agent-based model. So this is a screenshot from NetLogo. It's a model called wolf-sheep predation. This is an agent-based model, which means this model happens at micro level, and it means that each individual or each agent matters here, right? At this level, each agent, each individual matters. That's the reason why we have small symbols for sheep and for wolves. And they have specific rules to move across this space. And of course, when they meet, the wolf will just eat the sheep. And we have initial number for sheep, initial number for wolves, and sheep gain energy from food. The food is the background of this model. We have gray cells. It means that there is no grass. We have green cells, which means there is grass, right? When a sheep meets the grass, it will eat it and get energy to move. And also wolf gain from food, which means that if a wolf eats a sheep, it gains energy, and each wolf needs energy to move. Okay, and there is also reproduce rate for sheep and for wolf, so they can reproduce. Okay, and let me show you this model later maybe. So there is another model in NetLogo showing the same relationship between wolves and sheep at higher level using systems dynamic model. This model is called wolf-sheep predation duct. On the left side, we have the micro level agent-based model. On the right side, that's macro level data. Sorry, macro level model doesn't care about the each individual, care about the population of wolves and sheep. Okay, let me show you. You go to file. It's a part of models library of NetLogo, and here you can search wolf sheep predation, and here is agent-based model. Here is a duct hybrid model, which means shows agent-based model, ABM, and also the systems dynamics model simultaneously. Okay, let's open it. Okay, here we don't want this for now. So on the left side, we set up and go. You can say this small word is showing you the change of population of sheep and wolf. Each individual is important here, right? So this is ABM, agent-based model. On the right side, there is no, say, zero components for it, because this space is for you to address each individual, each agent in your model world. But when we're talking about aggregate model or systems dynamics model, individual doesn't care. Doesn't matter. We only care about population. So if you click setup and go, the system will run, the model will run, but we only have the situation or this diagram, this plot showing you wolf stock and sheep stock, or wolf population and sheep population. So yeah, this is a combination of ABM and also systems dynamic model for the same topic. You can say that they are created, these two models, they're created at different levels. The first one, they're created at individual level. The second one, population level or stock level. Okay, this is the end of the second video clip for this lecture. Okay, thank you.